Hello everyone, this is an interim presentation for ISD528. We are Team 13, and our project is the analyze and redesign of an electric mixer. An electric mixer allows users to grind meat and soft food efficiently at home. By loading ingredients into the hopper and turning on the device, the motor drives a screw and knife to push meat through the cutting plate, producing minced food of consistent texture. The primary customers are household users who value hygiene, convenience, and easy cleaning. The secondary customers are small restaurants and catering shops that require higher capability and longer operation time. Based on market analysis, our expected annual production is 50,000. The mixer includes three systems: a grading set, a motor with gearbox, and a support structure. It contains 14 components in total, as shown in the exploded cat view.
As shown in the first diagram figure, the main function of the electric mixer is to grind food. This is achieved through three key processes: feeding, crushing, and discharging the food. Supporting functions such as assuring convenience, assuring dependability, enhancing the product, and placing the sensors. Two assembly sequences were designed and compared. The first sequence follows a bottom-up approach, starting from the bottom plate and foot pads, then assembling the motor, gearbox, and finally the feeding and cutting components. The second sequence adopts a shell-based integration approach, where the shell acts as the main frame. Internal modules such as the motor, gearbox, and feeding unit are pre-assembled inside the shell. Then the bottom plate and foot pads are attached at the end. The comparison table shows that the sequence 2 performs better. It provides improvements in fastening and testing sub-assemblies, thanks to its integrated shell design, which reduces rework and increases assembly precision.
The function component mapping matrix for our meat grinder shows two value chains. First, the powertrain. Motor and gearbox transmit torque. The auger controls the torque and applies force to feed the material forward. Second, the cutting chain, which is knives, cutting plate, and adjustment components. The contact between them also helps prevent corrosion. The hopper helps prevent corrosion and simplify the operation. The housing, base, and rubber mounts primarily protect the user, facilitate cleaning, and enhance athletes. As shown in our bill of materials, the unit of cost in our product is 35.79 cents. Cost is primarily determined by the purchase component, representing approximately 70% of the total cost. Therefore, we can reduce cost and hardware by selecting multiple suppliers and using integrated motor reducers. For plastics, the unit price is low. Savings come from the DfA to reduce screws and assembly seconds. For the cutting slack, the cost is modest, but performance is critical, as it required finishing and tolerances, and designed for easy cleaning. The quad chart confirms the key priorities. High cost, high importance are the motor gearbox, protecting performance and reducing costs through screwing and integration. High cost and low importance are the housing, optimizing molding and reducing fasteners. Low cost, high importance components are the auger cutter plate and feed tube are protected for performance. Low-cost, low-importance components, hopper, bracket, and legs are targets for DfA consideration.
In our product family design, we focused on developing a modular electric mixer that serves both household and small commercial users through functional differentiation and component commonality. The key difference between these two customer groups lies mainly in capacity and throughput needs. Household user requires smaller batches and finer texture, while small restaurant benefit from larger hoppers and coarser cutting plate for faster operation. Despite these differences, both share the same expectation for safety, hygiene, and ease of cleaning. To achieve this, we designed a common platform where the motor, gearbox, screw, knife, housing, and electric component remain identical across all variants, providing consistent performance and simplifying manufacturing. Only two modules, the hopper and the cutting plate, are variable, allowing quick adaptation between fine and coarse grinding or small and large batch size. These parts connect to the shared platform through standardized interface, which make them easy to swap without retooling or changing the assembly process.
There are two variants for the meat grinder. the home variant, and the restaurant variant. The hopper on the restaurant variant is larger and can contain more meat at a time. The cutting plate restaurant variant has larger holes, making it output meat at a faster rate at the cost of some fineness of the meat. The modification enables the restaurant variant to hold more meat and process meat faster with minimal change to the design and assembly process of the original machine. The hopper's interface is a spigot and socket, allowing it to be installed by plugging the hopper on top of it directly. The cutting plate's interface involves a threaded nut that holds the plate in place. Both of the interface allows easy installation and removal of components. The assembly sequence of the original design can be modified to install the cutting plate and hopper at the final steps. The modified sequence shares 11 steps compared to the original design, which only shares 4, thus saving time, cost, and complexity.